Hello dear students, I welcome you back in online classes of Pathania Public School, and as we discussed in last week lectures about chapter 12, we covered it in two lectures, the revision of chapter 12, current and electricity, and for this week we are having chapter 13, that is magnetic effects of current, and the topics I am splitting of this chapter are as per your latest CBSE syllabus after the removal of few topics. So the first topic is magnetic field and magnetic field lines. Let us discuss this concept of magnetic field and magnetic field lines. Dear students, if we are having any permanent magnet like this I drawn here, it is having two poles, north and south. Then we know that if we place a magnetic needle around this magnet, a compass needle, then it will experience the presence of this magnetic field. As if I will place a magnetic compass here, then I know that the north pole of the compass needle will go in opposite direction, while the south pole of the compass needle will get attracted towards north. Similarly, if we are having a compass needle here, then north pole of the compass needle will attract to the south pole. So these deflections in the magnetic needle are confirming the presence of magnetic field around a bar, magnet, or any source of magnetic field. It may be a permanent magnet or it may be a current carrying conductor. Current carrying conductors are also source of magnetic field, and that is proven by Oersted in Oersted experiment. You must have seen it in my previous video lectures. So what is a magnetic field? What is the definition? We can write what is magnetic field. So definition of magnetic field is, it is the space around a magnet or current carrying conductor in which its presence can be felt. So space around जो space है, the three dimensional space around a magnet or a current carrying conductor in which its presence can be felt is known as magnetic field. तो जो magnetic field है इस बार magnet की ये चारों तरफ है, it is everywhere around the bar magnet. However, this field is stronger near the magnet, and as we move away from the magnet the strength of field decreases, but field is everywhere around this magnet up to very large distances. Even though the magnitude of field will decrease considerably, but field is present. So field is the space around the magnet in which its presence can be felt. Coming to the second point, what is field lines? Using small compass needles, or if I will keep a magnet on a cardboard or wooden box, and if I will sprinkle some iron fillings on the board, and if I will tap the board, then I will see these fillings will arrange themselves in a particular shape like this. So what this is indicating, when the iron fillings are aligning themselves in a particular direction. What is this direction? This is the direction. If I will move a small magnetic compass, then in the same direction magnetic needle will align itself, in which direction these iron fillings have aligned themselves. So these particular tracks, they are known as magnetic field lines. So these are the path which will be taken by a hypothetical north pole. If imagine, hypothetical means imaginary, अगर हम एक नॉर्थ पोल इमेजिन करें और उसको किसी भी पॉइंट पे अगर हम रिलीज करें तो वो किस डायरेक्शन में मूव करेगा, वो हमारे को उस पॉइंट पे मैग्नेटिक फील्ड की डायरेक्शन देगा. सो मैग्नेटिक लाइंस ऑफ फोर्स जो है या मैग्नेटिक फील्ड लाइंस जिन्हें हम कहते हैं या फिर लाइंस ऑफ फोर्स, ये लाइंस ऑफ फोर्स हमें पाथ रिप्रेजेंट करती हैं जिन पाथ पे अगर हम एक हाइपोथेटिकली इमेजिनरी नॉर्थ पोल इमेजिन करें तो वो जो फॉलो करेगा. एंड प्लस वन मोर पॉइंट विच इज वेरी इंपॉर्टेंट, दैट नो टू लाइंस विल इंटरसेक्ट ईच अदर बिकॉज टेंजेंट ड्रॉन ऑन दीज पॉइंट्स, any point on these magnetic lines of force, if we draw a tangent, it will give us the direction of magnetic field at that particular point. So it will as if two lines will cross, then at same point we can have two directions, which is not possible. So these are two important characteristics of magnetic lines of force. One, they are closed path, they do not, and second, they do not intersect. Reason, because at the point of intersection there cannot be two directions. Third point, you can see that near the poles crowding of the line is much greater comparing to the central area. So near the poles, so where the crowding of these magnetic field lines is more, it means that area is representing stronger magnetic field, stronger field, strength of field is more. And the area where magnetic field crowding is less is representing an area of weaker field. So that is also a property of magnetic lines of force. Now let us move towards our second point, field due to current carrying conductor. So as I told you that permanent magnet as well as current carrying conductors, they are also source of magnetic field, and in which direction they are applying field and how the magnetic field is forming around them, where are the poles related to that, we can reach on the results only after studying the pattern of magnetic field by current carrying conductors. So again, let us consider a current carrying conductor. Second topic, field due to current carrying conductor. So again, imagine a board placed in the plane perpendicular of the plane of board, and a conductor, current carrying conductor is passed through the center of board on which a battery is connected. And current is flowing through this conductor, let us say I current. In the same manner, if I will have my iron fillings sprinkled on this board and if I will tap the board when current is flowing, these iron fillings will align themselves in a circular manner. So which is indicating that magnetic field around a current carrying conductor is in circular direction. And in circular direction, what about the, in circular manner, what about the direction of magnetic field? So let me tell you, the direction of magnetic field is like this. And how do we find out this direction? Is by right hand thumb rule. If you point thumb of your right hand in the direction of current carrying conductor, suppose this is your current carrying conductor and this is the board on which iron filling is there. So if this is your current carrying conductor and current is going in this direction, upward direction, you pointing your thumb is in the direction of current, then look, curvature of fingers will give you direction of magnetic field. So on the left hand side of conductor, as you can see, direction of magnetic field is coming out of the board towards you. So left hand side of conductor, magnetic field is coming out, and similarly you can see that it is going inward as we move on the right hand side. If I'll show you the other view, the magnetic field of lines are like this. In the same manner, your conductor on board is like this, and magnetic field are in closed circular paths. Direction of current entering into the board on the right hand side of conductor and coming out of the board on the left hand side of conductor. So in this manner, closed concentric circles are representing direction of magnetic field and magnetic field pattern around a current carrying conductor. Let us move our attention towards current carrying coil or solenoid. So solenoid is a repeated number of turns of a single coil, and if we understand the pattern of single coil, then we can understand the pattern of magnetic field of a solenoid. So in the same manner, we considered the single conductor. Now let us consider a current carrying loop or a current carrying coil. That is number 3 topic, current carrying coil. So consider a coil attached to a battery, a key, and the current is flowing in this coil. Now, before I start explaining you magnetic field of a current carrying coil, take a pause here, take a break here, and imagine of this circular loop made up of number of small conductors. And let us consider such two small conductors on this coil. You can consider such small conductors anywhere on the loop, they will give you the same result. So if I consider this small segment as my straight conductor, then I will be having a field in same manner as I just explained in previous topic. So you will be having, I'll show you with red color, you will be having magnetic field in this manner, perpendicular to the plane, entering into the circle and coming out of the circle by right hand thumb rule, which we just applied on straight conductor. In the same manner, if you will consider here, now applying right hand rule here, the direction of current is in downward direction, so magnetic field will be entering in the interior of the loop into the board and coming out from the exterior of board. As you apply right hand thumb rule, when your current is in downward direction, then coming out and entering into the board. So again they will be in form of concentric circles, entering into the board in the interior of circle and coming out of the board in exterior of circle. So doesn't matter, you can take this small conductor of dl length anywhere on this loop and you will always find your direction like this. So this is indicating that magnetic field is entering in this direction and coming out from the opposite direction. If you will notice the direction of current in the loop, that is clockwise, and in previous bar magnet we had seen that magnetic field emerges out from north pole and enters into south pole. So the clockwise side of a loop is always behaving like a south pole, where if you will see it from the other side, it will be observed anti-clockwise and that side will become north. Look at my finger. I will keep rotating my finger in the same direction and you must be observing from your side it is anti-clockwise. So it will be north pole, and keeping the motion in the same direction without having any change, I am still moving my hand in same direction, but now if you will observe it, you must be observing clockwise direction, which means south. So if you are having a loop in which current is flowing in clockwise direction, then that side is going to be south pole, and if you will see it from the other side, it will become anti-clockwise for you and that will become north pole. So having this knowledge, you can draw the magnetic field pattern of a current carrying loop, and we can extend this knowledge for a solenoid What is solenoid? Solenoid is nothing but the combination of such coils in large number. So pattern of magnetic field of a solenoid is similar to the pattern of magnetic field by a bar magnet. So if current is entering like this, so current is like in, if you will see from the right hand side, the current is in clockwise direction. So this side is going to become south pole, and from this side current is in anti-clockwise direction. Anti-clockwise direction. So this side will become north pole. And magnetic field lines I can show you. In the interior of the solenoid, magnetic lines of force will travel parallel to each other, representing that uniform magnetic field is there in the interior of the coil. And at the outside, magnetic lines of force will go like this and like this, like this, and like this. So coming, emerging out from the north pole and entering into the south pole. Magnetic field pattern of a solenoid is very much similar to the magnetic field pattern of a solenoid. So permanent bar magnet or a solenoid, they have same magnetic field pattern. You need to understand how to draw this pattern and how the magnetic field line pattern is forming, because number of such loops which we just studied in previous lecture are connected here in this. The next and the last topic for today's video lecture is Fleming's left hand rule, or the force on a current carrying conductor in magnetic field. So dear students, if we place a current carrying conductor in magnetic field, then we observe that it experiences a force, and direction of force experienced by current carrying conductor depends on both the direction of magnetic field as well as direction of current in the conductor. And in which direction the current carrying conductor will experience the force in magnetic field is determined by Fleming's left hand rule, and this is also the principle of your DC motor or electric motor. So here let us try to understand. Let us have a magnetic field which we represent by B is in this direction from my left to right, and I am having a current carrying conductor in which current is flowing in upward direction. Let us say AB is the conductor in which current is flowing in upward direction. So what is Fleming's left hand rule? Fleming's left hand rule says that the topic is Fleming's left hand rule. So Fleming's left hand rule explains and gives us the direction of force experienced by magnetic field. So if we stretch thumb, first finger and second finger of left hand, do not forget it, left. Sometimes students apply right hand thumb rule. It is left hand, mutually perpendicular to each other. You can see they are mutually perpendicular. You do not do it like this. You are going to do it like this, mutually perpendicular to each other. They must be at 90 degree. Any two lines you can see they are at 90 degree to each other. So when we stretch our thumb, first finger and second finger of left hand mutually perpendicular to each other such that first finger is pointing in the direction of magnetic field. I had taken magnetic field B left to right shown by black arrows. First finger is in the direction of magnetic field. Then keeping first finger in the direction of magnetic field, second finger in the direction of current. Current is going in upward direction. AB conductor. Current is flowing in, or you can say CD conductor, because B we are already using for representing magnetic field. CD conductor. So the current is flowing in upward direction. Field is going from left to right. First finger, field, current, second finger. Then where my thumb is pointing? Thumb is pointing into the board. So this conductor will experience a force perpendicular into the board or paper if you are explaining it on your notebook. So if the direction of magnetic field will reverse, current is in same direction, but the direction of magnetic field reverses B and current is in same direction. Applying Fleming left hand rule again. This time you can see current is in this direction, magnetic field is there. So magnetic field, current, so now thumb is coming towards you. So thumb is giving the direction of force experienced by this conductor, which is now perpendicular out of the board or paper. Similarly, you can have any situation. For example, if you are having magnetic field which is represented by cross, uniformly placed crosses, and let us say this cross is representing magnetic field in perpendicular outward direction. So your B is in perpendicular outward direction and you are having a conductor in which current I, let me show it with the different color. So you are having a conductor which is placed in this magnetic field having current I in left to right direction. So applying Fleming's left hand rule, now as magnetic field is perpendicular outward direction represented by cross, so magnetic field is already in outward direction towards you and current is in, I can make it like this, magnetic field is towards you and current is in this direction, left to right. So you are observing that thumb is pointing in the downward direction. So direction of force on this conductor will be in downward direction. This conductor will experience a force in downward direction by Fleming left hand rule. So you can do practice on other examples and we can discuss about it in our tomorrow's live session. So take care of yourself and like always, thanks for watching. See you soon. Bye bye.